Welcome to the Chapter 14 and 15 Acids and Bases review. Before we get started, let's talk about what will be the test makeup. And there's going to be some matching, some multiple choice, and some problems. And as always, the problems usually count for more, so you want to make sure you get those done. And I always recommend saving the multiple choice for last in case you run out of time. All right, so let's get started on the next page. Here are some of the definitions that you need to know for the test. It is not all of them, but it is some of them. First of all, for an acidic solution, you need to know that in an acidic solution, the hydrogen concentration is greater than the hydroxide concentration. And of course, when you have an acid, you'll have a pH of less than 7. The next one is alkaline solution, and that means base. That's the same thing as basic. And in a basic or alkaline solution, your hydrogen concentration is less than your hydroxide concentration, and your pH is greater than 7. In order to calculate pH, we want to do the negative log of the hydrogen concentration. Remember, these brackets mean concentration. And a question that came up a lot over the lab, concentration is measured in molarity. So whether they're asking you to solve for the molarity or if they're asking you to solve for concentration, it means the same thing. We measure concentration in molarity. The hydronium ion is that H3+. Oftentimes we use the H+ instead, but they are used interchangeably, so they can be used the same. Hydroxide is the OH-. And remember, we recognize hydroxides as bases. So if you see that OH in there, it's a base. If a substance is amphoteric, that means it can act as an acid or a base. And we used a couple of examples in class, but the main example, or the most common example, is actually water, because it can act as an acid or a base depending on what it's reacting with. A neutralization reaction is when you have an acid plus a base and it yields a salt and water. And be mindful when we say a salt, we are not just talking about sodium chloride. It's any kind of salt. Remember, a salt is gets the cation from the base and the anion from the acid when it reacts. Titration, that's what we did our lab over. That's when we can calculate an unknown concentration with a known concentration. So as long as you know one of the concentrations and the volumes of the acid or base, you can calculate the other concentration. And then the last definition on the review was phenolphthalein, and that is an indicator. If it's in the presence of an acid, it is colorless, and if it's in the presence of a base, it is pink. Remember, it does matter what indicators you use when you're using a titration, because you need to target the pH range of your actual reaction. So let's talk about the characteristics of acids and bases. Both are electrolytes, so they will conduct electricity. If they are strong acids or strong bases, then they are a strong electrolyte. If they're a weak acid or a weak base, they will be a weak electrolyte. But nonetheless, they're both electrolytes. So let's talk about acids first. They have a sour taste. They react with active metals to form hydrogen gas. If you remember, we did the lab where we dropped the magnesium, we put them in the little metal cages, and we put the magnesium in the hydrochloric acid, and it bubbled, and we collected the gas in the tube. Well, the magnesium was an active metal, but we put it in a copper cage, so copper wouldn't be an active metal with acids because it didn't dissolve. pH is less than 7. Acids are corrosive, and if you have litmus paper, it will turn a litmus paper red. And bases, they taste bitter. They feel slippery. Think about soap when you wash your hands. It feels very slippery, and soaps are bases. They have a pH of greater than 7, and they are corrosive. And of course, they turn litmus paper blue. And so we have these characteristics. Remember, for pH, when we are looking to determine if something is an acid or a base, we always look at the pH value. On the homework quiz, some of you messed that up because you would look at the pOH value and you determined it based on that. So make sure you look at the pH value only and not pOH when you're determining if something is an acid or a base. So here we're practicing naming some of our acids, and I have them listed there for you, so I don't need to read through that for you, but I want to make sure you notice the difference between an oxyacid and a binary acid. And of course, the difference is one contains oxygen and one doesn't contain oxygen, and it's quite apparent that the oxyacid is the one that contains oxygen. And the naming system for that, from a review when we were doing naming, is if it is ending in ate, it goes to ick, and if it's ending in ite, it goes to us. Here are two good examples right here with nitric and nitrous. The NO2 is nitrite, so it went to nitrous. The NO3 was nitrate, so it would change to nitric acid. And of course, it's a binary acid. That just means it's hydrogen and one other element, no oxygen, and that's where we change the stem of the word to ick. So in this case, this is chlorine, so it'd be hydrochloric acid. And then the second part of this was to tell me whether it was mono, di, or triprotic, and that protic is how many protons in the form of hydrogen does it have to give. And if you look, this one had 1, so it's mono. The sulfuric acid had 2, so it's di. And phosphoric acid had 3, so it's tri. And so that's pretty easy to pick out. So to define the self-ionization of water and what are the products. The self-ionization of water, if you remember from the notes, was when we talk about when water breaks into ions separately. And so if you can show that with one water molecule and showing it breaking into H plus and the OH minus, or you can show it with 2 water molecules, and that's where we use that H3O plus, the hydronium and the hydroxide. And then the next one is you need to know the pH scale and indicate where the acid, base, and the neutral are. And of course, neutral is 7, exactly 7 in the middle. And if you remember, when we are neutral, that is when our hydroxide ions and our hydrogen ions, the concentration of those is exactly equal, okay? And when you're acidic, your hydrogen ions are greater than your hydroxide. And when you are basic, then your hydrogen ions are less than your hydroxide ions. So that's an important thing to remember. And so that is our pH scale. All right, so to define a strong acid and a base, if something is considered to be a strong acid or base, it means it completely ionizes in water, meaning it completely breaks apart into its separate components. And so if it is not listed in the things that we had you memorize, then it is going to be considered a weak. And so if it's a base, in order for it to be considered a strong base, it means it's going to be a group 1 or group 2 hydroxide, with the exception of beryllium. And then a strong acid are these 7 acids that I have listed here. If it is not one of these 7 acids, then it is a weak acid. And so that's just something you're going to have to memorize. And so I labeled these as we went through. NH3, not a hydroxide, so it's weak. The KOH and the calcium hydroxide, both group 1 and 2 metals. And so that would make them strong. HCl and H2SO4 are 2 of the ones we have listed as being a strong. And this last one right here is acetic acid, and acetic acid is not one of the ones listed, so it is a weak acid. So our 3 basic definitions of acids and bases, all 3 theories. You are responsible for knowing all 3 theories. The first one was the Arrhenius Theory, and that one was the one that we said was the strictest definition, meaning there's going to be fewer things considered to be an acid or a base under this definition. And it states that acids have to produce a hydrogen, and it states that bases have to produce a hydroxide when they're mixed in water. The second one was the Bronsted-Lowry definition, and it is our most widely used definition. It's the one when we usually talk about acids and base that we're referring to. And in that definition, the acids will donate a proton in the form of the H+, and the bases will accept the proton in the form of the H+. And then the last definition is the Lewis definition. And it is the broadest of the definitions, meaning there's going to be more things that would be considered to be an acid or a base under that definition. And that one's a little bit different because this time the acceptor is the acid and it accepts electron pairs, and the base will donate electron pairs. And so that one is the broadest definition. All right, so here we're going to define conjugates and give some examples. And just in case you don't remember, they are part of the Bronsted-Lowry definition, which was our most widely used definition. And the conjugate acid is what remains after the base accepts a proton. So in this case, here's my base right here. It accepted a proton, and then it came over here and it left H3O plus. So that would be the conjugate acid. The conjugate base is what remains after the acid donates the proton. So here I have my acid. It donated a proton, went over here, and this is what's left after it donated the proton. So that would be my conjugate base. So here's another example. I have HCl plus water. And so, of course, HCl, remember our acids always start with H, unless it's water. And so it's donating the hydrogen, and so it goes from the HCl to the Cl minus. So this is our acid, and what's left is our conjugate base. And then we have water, which is accepting the proton. And so after it accepts the protons, we have H3O plus, which is left, which is our conjugate acid. Little hint, if you see H3O plus on the product side, it's going to always be your conjugate acid. One important thing to remember is that they are an acid-base, they're called conjugate acid-base pairs, and they appear on opposite sides of the equation. So I have acid here, I have its conjugate base pair on the other side. I have a base here, I have its conjugate acid over on the other side. So they are on opposite sides of the equations. So we have a couple more definitions here. Difference between strong and weak acid or base, or concentrated or dilute. And strong means it ionizes completely. And of course weak means it only ionizes slightly. If I have a concentrated solution, it means I have a high amount of solute in my solvent. In this case, it means I would have a high amount of my acid in water. And then of course dilute is a low amount of solute in solvent. So what is a neutralization reaction? Remember, that's an acid plus a base making a salt and water. And just make sure we remember that's any kind of salt, not just NaCl. If it's a strong acid and a base, the pH ends up being 7. The neutralization reaction between HF, hydrofluoric acid, and potassium hydroxide would be the HF plus KOH. Acid-bases reactions are just a special type of double replacement. So we still do outside, inside together. And so when I put my inside together, I would get potassium fluoride, and then HOH together would give me water. When we do a titration, that's what we're doing as a neutralization reaction, and which means at the end point, we have an equal amount of hydrogen and hydroxide. So we just said this on the last slide. In a neutral solution, the hydrogen equals the hydroxide concentration. And at this point, at a neutral solution, they are both equal to 1 times 10 to the negative 7. So the pH would be 7, because if we took the negative log of that concentration, we actually get 7. So that is why that is the case. All right, so here we have a titration or a neutralization reaction, and I've showed it worked 2 ways. One is the way that I showed you in class, which was the formula. The molarity of the acid times the volume of the acid times the moles of hydrogen in the formula equals the molarity of the base times the volume of the base equals times the molarity of the hydroxide. Remember, when we're talking about the number of moles, we're talking about how many hydrogens are in the acid, in this case 1, how many hydroxides are in the base, in this case 1. And then we just plug it in. We do not have to change the milliliters to liters, because one's on top, one's on the bottom. Excuse me, so they will cancel out. And so when we do that calculation, we get that our molarity is 0.24 molar. You can also do it the stoichiometry way, for those of you that prefer that way. And you end up getting the same answer. You do volume times molarity, and then you do your mole to mole ratio, which in this case is a 1-to-1 ratio. And then when we do that, we get 0.006 moles of hydrogen, or in this case hydrochloric acid, and then we divide it by the volume and we get 0.24 moles. If you do the stoichiometry way, you do need to be in liters and not milliliters, and so just keep that in mind. But this is both ways. They will give you the same answer. It's just what your preference is. All right, so this one problem, we were supposed to find the pH of these 4 solutions. In the first 2, they give us hydrogen, so we can directly take the negative log. And when we do that, we find out that they are 8 and 9.6. So they are both bases. The second two give you the hydroxide concentration. So what you actually need to do is take the negative log to get the pOH. And then because, remember, pH and pOH equal 14, we can take 14 minus the pOH to get the actual pH. In this case, it's 11, and that would be a base. And then the next one, we get a negative log of that concentration. We get 11.4. So when we subtract 14 from 11.4, we get a pH of 2.6, which is an acid. Please remember, when we're determining if something's an acid or a base, we look at the pH value only. That's the only thing that determines whether something is considered to be acidic or basic. All right, so these two want to know the hydrogen concentration of a solution of one of them with the pH of 6.8 and the other one with a pOH of 2.8. So the formula is to get the hydrogen concentration is to take 10 raised to the negative pH. And remember, what we're doing is basically taking the antilog. And so because we took the negative log to get pH, we have to take 10 raised to the negative pH. So the first one is straightforward because it gives us pH. So we just take 10 raised to the negative 6.8. And then when we do that in the calculator, we get 1.6 times 10 to the negative 7. Because the pH only had one decimal point, we need one significant figure in our answer. So that becomes 2 times 10 to the negative 7 molar. Remember, we are talking about concentrations here, and so when we have a concentration, we need to put that molarity unit on the end. If you don't have that molarity unit on the end for a test, you will get a point taken off, at least a point. Probably could possibly be more than that. The second one is when we have a pH of 2.8. We can't go directly to it, so we have to subtract that from the 14. And then we get a pH of 11.2. So now we can raise 10 raised to the negative 11.2, and we get 6.3 times 10 to the negative 12 molar. Again, we have one decimal point, so we need one significant figure in our answer. So the correct way to write that would be 6 times 10 to the negative 12. And again, it's a concentration, so we need to put that molarity on it. So for a little something different for our jokes this time, follow through to the next slides, and I've got some cartoon jokes for you. Let's see if you get the second one. It's a little bit tricky. Well, that's it for this review lesson. Good luck on your test. Remember to study your notes, the review, and any of the worksheets we did in class, and good luck.